work? Okay, it works. Great. Okay, well, thank you very much for the introduction, and thank you to the organizers for the invitation to come present our recent result, where we design a bilayer electron system using 2D semiconductors to realize a wide range of tunable correlated electronic phases. What's important about the bilayer electron system is that we have a new degree of freedom, the layer degree of freedom. And it turns out that interlayer interactions between charges in different layers, can be fundamentally different than interactions between charges within the same layer. And under the right circumstances, this means that we can form things like spontaneous emergent bosonic order from an underlying fermionic order. And if you're interested in this, I'll remind you again at the end, but we have an archive recently up about this result. Okay, so first let me briefly outline my talk. First, I'd like to motivate why we're interested in using 2D semiconductors to study many-body physics. And then I will talk about how we build this bilayer electron system, how we use different types of optical spectroscopy to detect the different correlated phases that it hosts. I'll show you how we can build these emergent composite bosons, which come spontaneously out of fermionic order. And then finally, I'll show you that the bosonic order can coexist with fermions to form a Bose-Fermi mixture. Okay, so this result ties in very nicely to what is becoming a very trendy topic in the quantum matter community, which is the idea of on-demand quantum matter. And what is this? There are two aspects to on-demand quantum matter that I want to highlight. The first is programmability. So let me tell you something that is not an on-demand quantum matter, a block of aluminum. So aluminum is a superconductor if you cool it down to, I think, some few Kelvin. I don't know the exact number. But it's not an on-demand quantum material because you're not really controlling the interactions when you cool it down. You're just killing the thermal energy, which is destroying the underlying correlations. What we would like instead are materials where we have a high degree of tunability, which allow us to control the interactions in that material and to turn interactions on and off. And so this is the first aspect. The second is engineerability. So if I want to build a building which looks like a fish, I know that I have the right tools to do that. I can build it using reinforced concrete and steel and aluminum cladding. Is there sort of an analogy to materials where if I want to make a particular many-body phase out of electrons, I can design a device or I can do some nanofabrication to a material platform which introduces new quantum degrees of freedom, which I can control and use to realize whatever state of correlated matter that I'm interested in studying. And so I will try to make the argument now that 2D semiconductors fulfill both of these criteria very nicely and have some really desirable properties for studying many-body physics. So first of all, 2D materials, 2D semiconductors such as tungsten diselenide and tungsten disulfide, they are a single sheet, covalently bonded, as compared to a bulk semiconductor. If I put two charges next to each other in a 2D semiconductor, the electric field lines that connect those charges necessarily pass outside of the material, which means that there's no screening from the bulk. And so Coulomb interactions in 2D materials are especially strong. A really important first consequence of this for this presentation is that if I put an electron and hole next to each other, they will find each other and they will form a tightly bound exciton, an electron-hole pair. Okay, other helpful properties of 2D semiconductors of transition metal dicalcahydronides is that they have a direct band gap in the monolayer form. So that means that I can access the conduction of valence band edges optically. So I can send in a photon, it can be absorbed, promote an electron to the conduction band and form an exciton, and then later recombine and emit a photon. And this means that I have spectroscopic tools like absorption spectroscopy and photoluminescence spectroscopy to probe the electronic states at the low energy bands. The second important property is that in comparison to other 2D material platforms which are widely used for studying many-body physics, like twisted bilayer graphene, the carriers in TMDs, the electrons and holes, they have inherently large effective masses, which means that they are slow, they are relatively immobile, and this further promotes, alongside the strong Coulomb interactions, this promotes the emergence of many-body phases. So if I put together these different aspects, I can actually take a 2D material and I can stack it into a structure such as this, and I get a new device which has a wide range of tunability. This is a simple field effect device where I have a monolayer semiconductor, and then an insulating barrier, and then a layer of conductor on top. And these are capacitively coupled to each other, and I apply a voltage between the two of them, and I can therefore control the charge density in the 2D semiconductor layer. And so now, putting together strong interactions, excitons, and controllable charge density, it turns out that we can already see some first effects of many-body interactions in the exciton spectrum. This is another recent work from my group and the group of John Finley, where we show that we can form many-body excitonic states that consist of up to 20 excitations living across 10 different Fermi Cs, all bound together into a single quasi-particle. So this is a very interesting thing that can happen. You form these big states, and this really just shows you how strong interactions in 2D semiconductors can be. But we would really like to see spontaneous ordering of fermions absent some kind of optical excitation. And it turns out that interactions between charges that I just inject into the material themselves, not strong enough to do this on their own usually. They need a bit of help. And the push that we need to give them in order to form correlated phases is the introduction of a new periodicity into the system via a Moiré superlattice. So a Moiré superlattice happens when I take two layers of semiconductors and I put them together, and they must be slightly incommensurate. Either there's a small twist angle between them or there's a small lattice mismatch. But you form this spatial beat pattern between the two crystal lattices, and you have a new enlarged periodicity in the system, a Moiré pattern. And you can see here I've drawn a new unit cell, and the individual unit cells of the sublattices are quite small, about this big, and I have a new unit cell in my Moiré pattern, which is much bigger, and a new periodicity, a Moiré. And across the Moiré unit cell, you can see that I realize different stacking orders. They correspond to different registries between atoms and adjacent layers. And this has some really important consequences for the electrons that live in the Moiré. So first of all, as I move across the Moiré unit cell and the atoms line up with each other differently, the layer separation will be different, and the overlap between different orbitals will change from point to point in the Moiré unit cell. This means that tunneling between layers at different points in the Moiré unit cell is modulated, and this actually introduces a modulation into the conduction and valence band edges, resulting in an effective, an effective potential, a lattice-shaped potential, which can localize charges either in the conduction or valence bands. So I can make now a lattice of charges. And if I want to understand how interactions between charges on a lattice are going to proceed, the first place where you might start is with a simple Hubbard model like the Fermi-Hubbard model. So this is a single-band Fermi-Hubbard model. It has just two terms in the Hamiltonian. The first is intersite hopping, describing the kinetic energy of particles living on the lattice. And then there's an on-site interaction term, which takes care of the fermionic counting statistics, and it can be repulsive or attractive. In general, we're talking about Coulomb interactions here, so they are usually going to be repulsive in semiconductor systems. But even this very simple model captures some really important first results, the first being that at half filling, normally you would have a metallic state. If I put one particle per lattice site in the Fermi-Hubbard model, without interactions, I expect a metallic state. But if I turn interactions on, repulsive interactions, and I make them very strong, U much greater than T, then this metallic state transformed into a gapped correlated insulating state, a Mott insulator. And if I include other types of interactions in the system, like long-range interactions, nearest neighbor or next nearest neighbor, then I can form other kinds of correlated insulating states, like generalized Wigner crystals, which spontaneously break translational symmetry. Okay, so now I'd like to introduce the device that is part of the study. As I mentioned earlier, it's a bilayer electron system which consists of a monolayer of tungsten diselenide, which is separated from a Moiré heterobilayer consisting of WSE2 and WS2. They're separated by a thin layer of hexagonal boron nitride, which is a high K dielectric and prevents tunneling between the layers. And this means that the interactions between the layers are pure electrostatic Coulomb interactions. And I take the bilayer electron system and I embed it in a capacitive structure with both a top gate and a bottom gate. And by having both a top and bottom gate, that means that I can independently tune the chemical potential and the electric field in the bilayer electron system, which means that also I can effectively control the charge density residing in the Moiré layer and in the TMD monolayer. Okay, so now using these different controls, the electric field and chemical potential, I will show you that we can realize a few different kinds of correlated phases. The first is a Mott insulator consisting of electrons residing in the Moiré layer. Then I'll show you that we can modify this Mott insulator by pulling some charges from the Moiré layer into the monolayer to form bound states, interlayer excitons, and form a dipolar excitonic insulator. And finally, that this dipolar excitonic insulator is actually robust to charge doping, and we can form a Bose-Fermi mixture. Okay, so as a starting point, I'd like to introduce the spectroscopy of excitons in the sample so that you have the tools to understand how the different correlations are actually read out in the system. So this is the reflection contrast spectrum of a monolayer of WSE2. So this is, let's say, this part of the device where a monolayer actually overhangs the bilayer electron system and we don't have any contributions from the Moiré layer. So you can see at a gate voltage of 0, we have a charge neutral state where we have this state here, X, it's the neutral A exciton in WSE2, and then we have an excited state, a Rydberg exciton. And then as we add electrons or holes to the system, we either generate some negatively charged trions, so 3-body states, or some positive trions, which tell us that the sample is charged. On the other hand, if we look at the contributions of the WSE2 excitons to the Moiré heterobilayer, so now looking here where we just have the Moiré system, no monolayer, but we look at the spectral region corresponding to the excitons in the WSE2, we have a very different spectrum. Instead of having a single ground state exciton resonance at charge neutrality, we have 3, and this happens because we have a new periodicity in the system, which causes band folding and the emergence of new optical transitions. So we have these 3 Moiré excitons, M1, M2, and M3, and their evolution with charge doping is rather different from the evolution of the excitons in the free monolayer. So here, the excitons, you can see you move from one species to the next, but they evolve continuously. They can shift in energy continuously, and they change their oscillator strength continuously. Whereas here we have this rather discrete behavior, these discrete steps and cusps that happen at particular voltages. And I will convince you in a bit that these cusps correspond to band filling in the Moiré layer. Okay, and it turns out that the most useful exciton to study electronic correlations in the bilayer electron system here is the 2s exciton residing in the monolayer WSE2. So it's a bound electron hole pair. It's the excited state of the neutral exciton. And what's important about it being an excited state is that it has a relatively low binding energy and it has a relatively large radius. And this means that it's very sensitive to screening by charges that reside within the volume of the exciton. That it is some extended region inside and outside of that layer. And so more specifically, what it's detecting is actually changes in the dielectric screening caused by changes in compressibility, which you can understand from Fermi-Thomas screening. And so the 2s exciton is a sensor for electronic compressibility. And what this means is that when we put charges into the system, if they enter a metallic state, the 2s exciton should be screened away, it should disappear. And if those charges enter an incompressible state, an insulating state, then the 2s exciton should persist. And that's exactly what we see. So this is the spectrum of the 2s exciton as a function of increasing electron doping in the Moiré layer, while the monolayer itself is charge neutral. So I've labeled some particular points here where you can see that there's a strong exciton signal from the 2s exciton. So these correspond to 0, 1, and 2 electrons per Moiré unit cell. And so these are integer filling insulators residing in the Moiré layer. And in between these, you can see that the signal gets weaker, and then there are some, it's a bit hard to see from the projector, but there are some discrete points where it recovers a bit of oscillator strength, where it reemerges a bit. But between these special points, the 2s exciton disappears. So these points where the 2s exciton reemerges between 0 and 1, these are actually generalized Wigner crystals that emerge from long-range interactions. And then the half-filling nu equals 1 charge per Moiré unit cell insulating state, this has actually been determined to be a Mott insulator by previous studies. Okay. So now if we compare what's happening with the 2s exciton with what's happening with the M1 Moiré exciton, you can see that these discrete cusps that occur in the M1 Moiré exciton, these actually line up very nicely with the integer filling insulators detected by the 2s. And so these cusps and steps, these seem to be indicating the presence of integer filling insulators in the Moiré itself. So to summarize what these two excitons tell us, we have the 2s exciton, which senses compressibility of all the electrons in the system, and it works for any correlated insulator, whether it's a generalized Wigner crystal or a mod insulator or a band insulator. Oops. And then you have the M1 Moiré exciton, which is a local sensor of band filling. It detects, have you filled a Hubbard band in the Moiré layer? It doesn't really care about the electrons which might live in the nearby monolayer. So now what we'd like to do is track what these different correlated phases like the mod insulator are doing in the entire parameter space. So we have a back gate and we have a top gate, which we can use to tune the total density and the electric field in the system. These arrows are just a guide to the eye. In reality, the electric field and the charge density have rather complicated dependencies on back gate and top gate due to correlation effects and also contact performance. But generally speaking, as we go in this direction towards the diagonal, we increase the density, and as we go towards the anti-diagonal, we increase the electric field. And so an electrostatic phase diagram is just a map of the 2D gate parameter space, where at each pixel we take a spectrum and we extract some information from the spectrum, for example. Here's just the integrated strength of the 2s exciton. So everywhere you see a dark line in this electrostatic phase diagram is a place where there's a correlated insulator or an insulating phase, an incompressible phase. And from the phase diagram, we can extract the line cut, this black dashed line. We can look at what the excitons are doing along that line in the parameter space. So this is the data that I showed you before, where we have the nu equals 0 and nu equals 1 insulating states and the generalized Wigner crystals. And then if we track the other exciton resonances in the system, you can see that if we look at the trions in the monolayer, well, they're not there because the monolayer is charge neutral at this low electric field value. And if we look at the M1 Moiré exciton, you see these cusps corresponding to the integer filling. Okay, so now, as I mentioned, we're going to start with this mod insulator, which I just showed you, and then we're going to apply an electric field, and we're going to pull some charges from the mod insulator in the Moiré up into the monolayer. And these will leave holes behind in the mod insulator, and the holes can bind to the electrons to form these dipolar excitons. And I'll show you that these form an insulating state. So now, taking the electrostatic phase diagram and looking at a line cut at higher electric field, you can see we once again see the nu equals 0 and nu equals 1 insulating phases detected by the 2s exciton. If we then look at the other excitons in the system, the trion, this is a bit different. You see, now we actually see a trion signal indicating that between these states and generally across this line cut, the monolayer has charges in it. But curiously, they actually disappear abruptly. The trions disappear abruptly when we enter this correlated insulating phase detected by the 2s. So this overall incompressible phase somehow involves sucking the charges, the free charges out of the monolayer. What's happening is that exactly at this point, you have charge balance between the holes injected in the insulator and the number of electrons which have been injected into the monolayer. And at charge balance, you form these neutral excitonic creatures. And the electrons become immobilized. They're no longer free to form trions, and so you lose trion oscillator strength. And curiously, if we look at the kink in the M1 Moiré exciton, you can see that now this no longer aligns with the overall incompressible phase, and that's because this is a distinct phase now. It's a mod insulator, which is living underneath some uncorrelated electrons living in the monolayer, which you can see from the existence of trions at that same gate voltage. Okay, so the story so far is that we have an underlying mod insulator which stabilizes the dipole formation. The dipolar excitonic insulator is charge incompressible. And I want to really highlight that these excitons, these interlayer dipolar excitons, these are not the same as the optically excited excitons that we're using to sense the charge order. They are an electron residing in the conduction band of the WSI2 and a hole residing in the first Hubbard band in the conduction band of the heterobilayer, the Moiré layer. Okay, so finally, I want to examine what happens when we start with the dipolar excitonic insulator and we either add some electrons or we remove some electrons from the system. So you can see that if we track the 2s exciton and we add some electrons, that there's a continuous loss of 2s exciton signal strength. This means that the screening of the system is just gradually changing, the compressibility is changing gradually. But if we remove some electrons or add some holes to the system, there's a sudden change in compressibility. The system seems to destabilize and we lose our incompressible phase. And so we have a simple microscopic picture to understand what's going on. So we start from the dipolar excitonic insulator and we add an electron, and this results in, whether we add it to the monolayer or to the Moiré layer, this results in just a free electron living next to these dipolar excitons in the monolayer. And it provides some screening, but it doesn't fundamentally destabilize the mod insulator, which gives rise to the stability of the dipolar excitonic insulator. And this alone, this already implies the existence of a Bose-Fermi mixture. On the other hand, if we dope the system with holes, this always results in the liberation of a hole in the Moiré layer, which can then run around wreaking havoc, destroying the underlying Mott phase, destroying dipoles, and this leads to the destruction of the incompressible phase and this asymmetric behavior. And so we want to understand what is the phase diagram of this Bose-Fermi mixture. We understand this theoretically. This is a mean field calculation performed by the group of Michael Knapp by Wilhelm Kadov. So they perform mean field calculations where they keep track of all the charges in the system and whether or not they are paired into dipoles. And you can see that in this wedge-shaped region in the electrostatic phase diagram, you have this doped Bose-Fermi mixture where we have dipoles. And it's bounded on the left by the pure dipolar excitonic insulator, the charge balance case. And it's bounded on the right by the Mott insulator residing in the heterobilayer. And this theoretical phase diagram actually matches very nicely with the experimental phase diagram, where we've extracted using the 2s exciton, the incompressible phase shown in these orange dots. That's the dipolar insulator up here. And then the Mott insulator, which we are deriving from the kink in the Moiré exciton. Okay, so just to summarize and conclude, we built a bilayer electron system with a single Moiré layer and a Moiré free layer. This allowed us to build different kinds of correlated electronic phases. We study the bosons, we study the Bose-Fermi mixture, and we would like to eventually study an extended Bose-Hubbard physics because we can only reach a certain density of bosons in the system. So this is actually one of the important limitations here. So the system that we study here, there's this fundamental asymmetry because we have a Moiré layer and a monolayer, which gives us this peculiar doping instability. Also, like I said, the boson density has an upper limit, and this is because, you can imagine, if I want to achieve a boson filling factor of 1 per Moiré unit cell, I'd have to start with a Mott insulator and then pull all of the charges from the Mott insulator into the monolayer, and then I have no underlying Mott insulators to stabilize the phase. And finally, the bosons in this system are probably mobile because they inherit mass, the relatively light mass of the free carrier living in the monolayer. And if you want to know how we overcame these limitations and did some much more fancy, exciting stuff, please see the poster by Amin Ben-Meni, which will be presented tonight. Here's a sort of teaser. Thank you very much for your time. Thank you to all of the collaborators who worked on this project, especially to Amin, who did a huge amount of work, and all of the students in my group, and Professor Finley, the group of Michael Knapp, the Crystal Growth collaborators, and the funding agencies, and all of you for your attention.
Thank you for this fascinating talk. Other questions? Yes.
I said.
Nathan, thank you very much for this beautiful talk and also presenting these beautiful results. I have a question about the cusps.
The cusps, sure.
About the energy, what you see. Do you understand this energy jump? And also, does it depend on if you're in the correlated or uncorrelated state?
Both good questions. So the microscopic picture of what's happening at these cusps is not completely clear, but it's a combination of effects. There's a change in screening. So I want to be really careful here. These are Moiré excitons arising mostly from the WSI2 layer in the heterobilayer, while the electrons that we're injecting at these cusps are residing in the WS2 layer. Nevertheless, because it's a heterobilayer, the layers are hybridized, so there's some amount of this exciton which is actually coming from the WS2 orbitals. So there's a screening effect, which actually gives us, I'm not sure if you can see, but at the cusps, there's an increase in oscillator strength. This comes from reduced screening. And then the energy jump is associated with change in the effective mass as you fill to the next band. So it's a renormalization effect, and that only happens because of the hybridization, that you detect that with the exciton and the complementary layer.
Rudolf von hinten.
Yeah, I just wanted to make sure what you call bosons and fermions in your boson-fermion mixture. So do you call bosons the bound pairs of two fermions?
Yes, they're composite bosons.
Because I'm always cautious about, because you have a bound state of two fermions, and this you still have to describe by an anti-symmetric wave function, because it consists of two fermions. So I'm always a little bit critical in calling this a boson. Is it the same in superconductivity?
Yeah,
Where you have Cooper pairs, and Cooper pairs you have to describe by an antiferromagnetic wave function, because it consists of two fermions.
Nevertheless, they can enter a degenerate macroscopic
has
process. So they behave a bit like bosons
so
in a
it's spin
sense.
singlet, so you have spin zero.
So this is a discussion we had quite a bit with Michael, whether or not we should think of these as bosons, whether the counting statistics will be like bosons or not. Okay. We don't know exactly what is the factor that determines whether these will behave more like fermions or like bosons, to be honest.
Yeah, in BCS, when you are writing down a BCS ground state, and in terms of creation operators, all powers higher than 1 are disappearing, because you have to take into account Pauli principle, because the state is built up by fermions, actually.
Yeah, there is some evidence that these are behaving more like bosons coming from a related system, which is just a simple Moiré bilayer where you can have higher than 2 occupancy of interlayer excitons per Moiré unit cell, not necessarily residing in different bands. It seems that they can, the degeneracy is not.
Okay, we can discuss in the coffee break.
Yeah, it's not a simple answer, unfortunately.
Time for one more question, otherwise. Yes.
Thank you, Nathan, for the really interesting talk. I was wondering if you go forward a few more slides, you showed this, exactly this one, sorry.
This one.
You showed this nice plot of your voltage space.
Yeah.
But then you take and you explain that the axes of the change of the electric field and the density aren't exactly along VT and VB, but then you take the line cut along VB. I was wondering why you don't want to take it along the line of the change of density.
Because that line is not exact. This is an exact line. I can relate this to a physical quantity, which is the backgate voltage. If I take this diagonal, or whatever the calculated diagonal should be, it's actually not going to correspond across the phase diagram to density. Calibrating the density is really not straightforward, because we have Schottky contact, because correlation affects open gaps, correlation gaps, which mean that there's some energy penalty to cross it. So there's really not a linear relationship between some linear parameter in this direction and the density.
Thank you.
Mm-hmm. Okay, then let's move further discussions to the coffee break, and let's thank Nathan and all the speakers of this